Well, hello there. So let's now look at how to solve a circuit and turn it into its equivalent circuit. So again, remember we have two kinds of equivalent circuits, the Thevenin equivalent and the Norton equivalent. And the solution process is similar for both, so we'll do them at the same time. The Thevenin equivalent takes any linear two-terminal circuit, so any combination of circuit components with two wires coming out of it, and the theorem says that we can replace any complicated circuit with a simple circuit consisting of a voltage source, the Thevenin voltage, and a resistor in series, the Thevenin resistance. The Norton equivalent takes the same original complicated circuit with two terminals and replaces it with this circuit with two parts. This time it's a current source, the Norton current, and a resistor in parallel, so that's the Norton resistance. But let's look at the details now. So we need, for either the Thevenin or the Norton, we need two numbers. For the Thevenin, we need the Thevenin voltage and the Thevenin resistance, and for the Norton, we need the Norton current and the Norton resistance. So we have to do two analyses. Sometimes people get kind of tired out and they do the first one and they stop. So make sure you do both analyses, get both numbers when you're doing these problems. So let's see how to find the Thevenin or Norton equivalent circuit. So this is method 2 in the book. The book gives us 3 methods, and we're using method 2 as I think the simplest one and most commonly used. So we're going to start with that, and we'll look at the other ones for special cases coming up. So here you have to do one analysis because you have to find either the Thevenin voltage or the Norton current. So we have to find a voltage or a current. And these pictures show how we take our original complicated circuit, and if we do an analysis to find the open circuit voltage, which means nothing connected to the terminals, whatever the voltage is between A and B, that's the Thevenin voltage. So normally we would do a node analysis where we would put the ground node at node B, and whatever we get at node A is our Thevenin voltage. If we're doing the Norton, the easiest thing is to short the terminals together and find the current between the short-circuited terminals on our original circuit. So this is usually done with a mesh analysis, because if we short-circuit these, we've got a mesh on this end over here, and that mesh current is our short-circuit current, and that short-circuit current is the Norton current that we need. So depending on if you're doing Thevenin or Norton, you have to do one circuit analysis on the actual original circuit. The second step is the difference here with method 2 is how the second step comes in to find the Thevenin resistance or Norton resistance. They're the same. And so this is the easier method because we don't have to do a full node or mesh analysis. What we do is we take the original circuit and we get rid of all of the sources. We zero them out, which means we replace voltage sources with short circuits, because when you measure across a short circuit you get 0 volts. And we replace any current sources with open circuits, because if you cut wires you have 0 amps. And so this simplifies the circuit so that nothing is going to be left except resistors. And then we can analyze that circuit for the equivalent resistance of that mess of leftover resistors, and that equivalent resistance is the Thevenin resistance. So we take our circuit, we modify it by zeroing the sources, and we find the resistance. So this is the easiest one because it just has one node or mesh and then one equivalent resistance analysis. But it doesn't work if you have dependent sources, which are the diamond-shaped ones. So if you have a circuit with dependent sources, you have to use one of the other methods. There are 3 methods that we'll see today. Okay, so let's do an example. And this is an example of finding the Thevenin resistance of this circuit shown here. So we've got an original complicated circuit. It's got 2 wires coming out, A and B. And we want to find the equivalent resistance. So none of these are dependent, so we can use this method. We redraw this circuit with the sources zeroed. So to make 0 volts here instead of 16, we replace it with a short circuit, the wire right here. To make this 4 amp current source become 0 amps, we cut it out. We replace it with an open circuit. So we've got the open terminals right here. And now all we have are resistors left. So we need to find the equivalent resistance that we'd get if we measured with a resistance meter between A and B. So we have to find series and parallel pairs and reduce one by one. So because of this short circuit here, this 50 ohm and this 50 ohm, they're now in parallel. Might be easier to visualize if we dragged this one up and around the corner, but their heads are connected, same node, and both tails are connected to this node. So these are in parallel. So we can replace them using the parallel equation 1 over the 1 overs, and we get this 25 ohm. Replacing both of these. We still have the 30, still have the 35. Then we can look between A and B. The 25 and the 35 are in series, so we can replace those with those added together, and then that resistor would be in parallel with the 30 ohm. So 30 ohms in parallel with 25 plus 35 gives us our final answer. Might have to draw the circuit a few more times, but we get 20 ohms when we're done. Okay, so let's do that again on a little bit more complicated example. So here is our original circuit, and the red box shows the part that we're going to replace with the equivalent circuit. Notice that there are the two terminals, A and B, and this is a load resistor that just shows what we're connecting to our equivalent circuit. So the load resistors always go away. They're never part of the analysis. So to find the Thevenin resistance, we take our original complicated circuit and we zero the sources. So we're going to take our 24 volt voltage source and replace it with a short circuit to give us 0 volts. Take our 7 amp current source, replace it with an open circuit to give us 0 amps. And we're left with a bunch of resistors. So we need to find the equivalent resistance of these resistors here from the point of view of A to B. So again, we have 6 in parallel with 12 because their heads are connected to the same node and their tails are connected to the same node. So 6 in parallel with 12, and if we replace those with a single resistor, we would have that in series with 2. So the shorthand for this is 2 plus 6 in parallel with 12, and the 1 over the 1 over equation is written out here. And we get a total of 6 ohms. So you can check those numbers yourself if you are rusty on your parallel and series. We get 6 ohms for the Thevenin resistance or the Norton resistance. The next step is to find the Thevenin voltage. So we go back to the original circuit with the sources back in place, and we solve for the voltage between A and B with the load removed. So remember, we're always removing that load resistor if it's shown. Sometimes it's not. So the easiest thing is to do a node analysis. We put the ground node down here so that it's at B, and then whatever we get for node A is going to be our Thevenin voltage. There's a configuration that comes up a lot because we're removing the load, and it's shown here. We have a 2 ohm resistor going to terminal A, but this open circuit voltage is what we're looking for at voltage A, what we would measure here, but there's only one branch. So after a while, you'll get used to these and you'll say, oh, the voltage at A is the same as the voltage here at C, and that's the way you want to do it. And so we do node analysis to find VC, and that's our Thevenin voltage. If you forget, we can do Kirchhoff's current law. As we see here at node A, going out, we have VA minus VC over 2, and that's the only branch, so that has to equal 0. So that proves that VA equals VC. And once we realize that, we can go back and just do the analysis at VC here. We have another node here, but it's 24 volts. We've got the ground node down here, so hopefully your node skills are good. If not, you can review those videos. But if we do KCL at the VC node, we get VC minus 24, VC minus 24 over 6, plus VC minus 0 over 12, plus 7 going out equals 0. And we can solve that for VC, which is VA, which is V Thevenin, negative 12 volts. So don't forget, finish these problems. Sometimes people get halfway through and they just get tired. So we have the Thevenin resistance of 6 ohms, the Thevenin voltage of negative 12 volts. So those are our two numbers. Then we draw the circuit. So here it is. I usually just draw it like this with a plus minus, plus on the top, minus on the bottom, the resistor up here, and just write down 6 ohms and write down negative 12 volts. That's great. Done. Some people don't like negative voltages, so you can switch the polarity here and write it down as positive 12 volts with the minus on the top. It's the same circuit, so if that makes you happy, go for it. So that was method 2. It's the easiest, I think, because we just do one analysis, the open circuit voltage for the Thevenin voltage, and then we do equivalent resistance for the Thevenin resistance. And so there are some other methods that we'll look at next. Everyone uses the open circuit voltage analysis to find the Thevenin voltage. So it's the same analysis here for any Thevenin approach. And method 1 finds the Thevenin resistance by finding the short circuit current, which is our Norton current, and then uses Ohm's law here to find the Thevenin resistance from the Thevenin voltage and the Norton current. And method 3 uses a load that is a voltage source instead of the load resistor and solves for that. So we'll see that in a second. Both of these methods work with dependent sources, so that's the main advantage to them. They're a little more complicated analysis. This is method 1, the first one that the book talks about in chapter 3. And so it takes 2 circuit analyses. We analyze the entire circuit once to find the open circuit voltage using probably node analysis. Then we analyze the circuit again with the terminals shorted together to find the short circuit current. And then we know that the Thevenin voltage is the open circuit current, and the Thevenin resistance is the Thevenin voltage divided by the short circuit current. And we could also get the Norton current. It's the short circuit current also. So with these 2 analyses, you get the Thevenin or the Norton really easily. This method works for any circuit, whether it has dependent sources or not. And it can also be used experimentally. You can see here we've got a meter hooked up. So if you wanted to find the Thevenin equivalent of something like a car battery, that's not something you can analyze. You don't have a schematic of how it works. It's just a thing. You could sit down with a voltmeter and you could take these 2 measurements and find the Thevenin equivalent. This is dangerous though, so it's important to point out that measuring the voltage is pretty safe. Voltmeters have high resistance, there's not much energy going transferred here. But this current measurement where you short the terminals together, if this is a car battery, you're going to get hundreds of amps running through those things, and you might arc weld your battery cables together or something terrible. So this is a dangerous thing if you really don't know what it is. If it's a black box with wires coming out, don't just touch them together. That's dangerous. So it's not safe. The book shows you can actually add a resistor in series with this measurement to safely measure it, and then you add that equivalent resistance on. So there is a way to do this experimentally if you need to. Let's look at this method 1. To find the Thevenin equivalent. So again, this is what we just looked at. We have this same circuit here, the load resistor, and for method 1 we find the Thevenin voltage, the open circuit voltage. So this is the same node analysis we just went through, and we find the open circuit voltage of negative 12 volts. And now instead of doing equivalent resistances, we find the short circuit current. So we've changed our circuit now by putting a wire connecting these 2 terminals, and we have to find the short circuit current. So this is the analysis from the book. They do a node analysis to find this new VC prime because it's a different circuit, so a different voltage here. And then they use Ohm's law to find ISC. Traditionally, you would see something like mesh analysis, because if you did mesh in this mesh, that's the ISC that you're looking for. But here with this current source, it's a little bit more complicated, so they took a shortcut. But either way, use your methods to find the short circuit current. And then once we have the open circuit voltage and the short circuit current, we can find the Thevenin resistance, or the Norton resistance if you wanted. It's the same thing. 6 ohms, like we saw before. Thevenin voltage, open circuit voltage was identical to the time we did it with method 2. And we get our final Thevenin equivalent circuit. So don't forget to draw the circuit when you're done. So that's another way. It's not too hard. If you have a computer program that can do your analysis, this is a good one. It's usually easier to find a computer program that can solve for voltages and currents rather than equivalent resistances with zeroing out and things like that. So this method 1 is one that is a nice one to work with computer programs. All right, so the third method, do you need a third method? Maybe not, but here's the third method that the book has. Here's our original complicated circuit, and we deactivate the independent sources by zeroing them, and then we add a voltage source here. So if the circuit contains both dependent and independent sources, you can find the Thevenin resistance by zeroing the independent sources. You add this external source, and then you solve that circuit, which is simplified because it doesn't have the independent sources, the round ones. It has the diamond ones still. And we can find the Thevenin resistance from the applied voltage. Often people use 1 here and divide it by the current that you solve in your analysis. So that's the third method that you could do. Sometimes a little bit simpler than method 1, and it works with dependent and independent sources. Okay, so that's the Thevenin and Norton example. You'll get to do more for homework. Remember, each circuit requires 2 numbers. So if the problem says find the Thevenin equivalent or the Norton equivalent, you need 2 numbers. It's 2 analyses. And if you find 1, if you only remember how to do Thevenin, you can always solve for the Norton and vice versa, because IN is VTH over RTH, and you can use that to solve for either, and Rn equals RTH, so the same resistance for both. We're taking an actual circuit with 2 wires and converting it to either this or this. All right, I hope that helped, and I will see you in the next video.